I carried the idea to build myself a rotating table for a long time. So finally I decided that I actually waited long enough and I built one. This video will cover all steps from selection of the electronic parts, design of the housing and mechanical parts, and then finally writing code to bring some rotating life into the final result. Chapter 1. The specs. First, I wanted to be as big as possible but still printable on my Prusa Mini. Well, that one is a relatively simple one because my Mini has 18 cm by 18 cm print bed. Second, the rotational speed should be adjustable. So that means I wanted to be slow and fast. Right. Third, the absolute speed is actually not so important, rather the precision of the motion and the consistency. So I want it to be smooth, I don't want it to be jerky all the time and checking around and everything is shaking like crazy. Fourth, I want it to be rotating in both directions and I want to control that by clicking something. And fifth, ideally there should be a single AA battery to power the entire table for simplicity reasons. Chapter 2. The electronic parts. First, the sourcing of the parts. As for the engine or the motor, I had a stepper motor in mind, as this would give me a great deal of control with very little effort. It is very easy to rotate in both directions and control the speed on top. I roamed the internet a bit and stumbled quickly over a small stepper motor, the 28 BYJ48. What a name! In retrospect, probably not the best motor, as I totally ignored, for example, the fact that it has a gearbox built in, and the specified revolutions also ignored this gearbox completely. But there was a supplier that also included the driver module, and it was a good enough thing to start with. The brains of the project would be definitely based on an Arduino-like clone, as I had very good experience with the stepper lips in the past. Still had a Pro Micro lying around, a cheap 32U4 based model from an earlier build project of Tom Stanton's awesome joystick that has been in the meantime evolved away from a pure stick into more of a yoke version to cope with my aircraft preferences in Microsoft's Flight Simulator beta. And yes, it is currently very broken. Shout out to Tom for his awesome projects and his work in general. And if you don't know him, where have you been? I mean, seriously. But honestly, every small Arduino would work fine here. And finally, the power supply. As stated above, I'm living in my kind of fantasy world where power is not an issue at all and where simplicity is king. I don't want 4 batteries to be tangled up in every single project I do and then virtually disappear forever from my stockpile. So I like to keep things simple and minimal and reduce the number of batteries wherever I can. This one was a very bad decision, as the motor draws a lot of power and simply powering all parts and the motor from one battery is not enough. Especially as I wanted to drive the supply lane with 5 volts, which means the voltage of the battery needs to be boosted from 1.5 or rather 1.2 in case of a rechargeable battery to 5 volts. The bigger the voltage gap, the more amperes need to be pulled from the primary power source to substitute the voltage difference. It is possible to achieve this, but only if all components, including the battery, can handle the demands. But it definitely gets more challenging to make it work. Well, in hindsight, I was actually doing the opposite of keeping it simple. I should have just added another battery from the start. Lesson learned. Anyways, I was first using some voltage boosters I had still lying around, but the first attempts were unspectacular and actually nothing was working. Turns out, boosting from as low as 1.2 volts is actually not so simple and common for those circuitries, and it took me a couple of attempts to find a circuitry that was able to maintain even the unloaded 5 volts from the battery. I finally went to Pololu, which has a great range of cheap, small but yet powerful power conversion boards available, and a couple of them are also capable of boosting from 1.5 or 1.2 volts, which was exactly what I needed. Last but not least, for controlling the speed, a simple potentiometer would do. I always have some basic ones in stock for these kind of projects. And then for changing directions, there is the need for a small switch, and I also have those in stock. And then finally, I wanted to have a flip switch to disconnect the battery from any consumer at all, so that the batteries are not drained over time when I'm not using this rotating table. Chapter 3. The 3D model. So with my list of components finalized, it was time to start designing the case. That includes a bottom part, the static, a movable top part, the rotator, a mounting plate or control plate for mounting the potentiometer, the button and the flip switch, mounts for the motor and the rest of the parts, a suspension for the rotator so it can rotate freely with the ability to support even a bit heavier models. And that's it. As always, I did my design work in Fusion 360. For this workflow that I'm using, it is very recommended to mock up all the components that need to be mounted later. This way I was able to shift and push the parts around until I found a setup that made sense to me. Except the positioning of the motor and the controls, only the placement of the Arduino was important, so that I would be able to mount USB cables to it later to program it. To keep it simple and also flexible, I decided against precise mounts for all components and instead printed a couple of these profiles that I glued into the base and then fixed the PCBs with zip ties. For the gears, I used the Fusion gear scripts. I didn't pay too much attention in the beginning to the ratios and the sizes of the two just yet, as I was certain they would be off anyways. And to be honest, it's simple enough to print other ratios later. I am not aware of a proper way to print the outside gear, which is facing inwards, so I designed just a negative shape and subtracted that from the rotator internal parts. I am no mechanical engineer, but I'm pretty certain this messes up the weird magic that gears involve. But YouTube is full of tutorials using this approach, so it cannot be bad, right? Chapter 4. The build. So this model after printing is relatively simple to clean up, only a bit of support material under the bearings. Then mounting the parts for the control panel. And then finally mounting the bearings. Initially I wanted to screw those in place, but that was actually not necessary. So as mentioned in the beginning, I didn't want to fix all the positions of the components already in the design, so that is why I'm now gluing those frames into the base and then attaching the components to those frames. So I have to say this looks relatively tidy and organized. And I was actually hoping to keep this standard for the rest of the wiring, but you will see in a moment that I, to my own personal judgment, think that I failed with that. Anyways. At this point I decided that it is time to check if my power supply circuitry actually works before I continue any further magic with the motor and the controls. So as you can see, I pulled out the big guns and started crimping. I definitely favor cable connections that are removable later, either for debugging or for decomposition of my projects, but it's definitely more work to get it done in the first place. And again, mental note to myself, I should really think about cable management up front and not like here, make it up while I'm going, because you can already see the mess, evolving. Now, this is the moment in time when I realized that I have a real problem. I noticed that touching the motor slightly was enough to let the LEDs of the other components blink, which means that there's a serious problem with the voltage supply level. And here the journey began. Well, to be completely honest, this was already the second attempt to make it work. Going back to the intro, this was the power supply I was first using. But it didn't matter how hard I tried to adjust the output power, nothing was coming out more than those 1.2 volts from the battery directly, which is at least something. The outcome of the second attempt you have already seen now. And then I went to Polulu and got myself a really tiny and really nice circuitry that can provide, even from as low as 1.2 volts, clean 5 volt outputs that are even adjustable. Put it all together and here is the final result. Yes, the cables are a mess, but it is working. However, with one battery cell it was still very weak and the motor easily stopped, which is why I came to my senses and just added a second battery, which solved all my problems. And this brings me to the last chapter for this project, writing code for the Arduino. Almost all electronic aspects of this project are very simple to handle with an Arduino. In fact, every microprocessor in general. Only driving the stepper motor requires a bit more effort, as 4 output pins need to be driven correctly to turn the 2 coils of the stepper motor. For this, also a notion of time is necessary to be able to drive a certain amount of steps within a given time, usually referred to as speed. Luckily, all of this is covered by a basic stepper motor library called Axle Stepper that can be added using the plugin manager. This library can also accelerate and decelerate gently if needed. The rest of the controls are the switch, which requires only a digital input, and the potentiometer that requires an analog input. What you see here is the entirety of code that runs the rotating table. Let me quickly go over the different components. At the top, the stepper library is included. Next, I define all my pin macros to have all the pin definitions in one place in case I need to change it later, something I definitely recommend doing. At last, I also define the absolute max speed for the motor. Next, some variables including the stepper object, and then already the setup function that every Arduino project has at its foundation. Here, I set up the stepper default settings and configured the general purpose input-output pins, also referred to as GPIOs. The supply lines for the switch and the potentiometer I'm also driving as Arduino outputs, so I need to set them up here as well. And then the loop function, which is called by the Arduino internal code over and over into all eternity. Here, for each pass through, I call the stepper service function that keeps track of time and when it is necessary to move the motor one step further. Next, I'm simply reading the analog line coming from the potentiometer and set the speed for the stepper. It would be possible to program this in a much smarter way and only change the speed when there is a significant change in input level, but honestly, this is not worth the time spent on it and way simpler this way. And finally, I'm checking whether my push button has been pushed, and if so, I reverse my internal reverse variable that steers the rotation direction. Here I'm doing a bit of extra effort to only re-trigger a change of direction when the button has been released after a push. Otherwise it would result in potentially many direction changes within a very short amount of time and unknown outcome of rotational direction, and that would be very unsatisfactory. And that already wraps up the code necessary to drive this little project. And that concludes the video. Writing code was the last step of the process. All in all, it took me a bit longer than initially expected with all the issues that I had with the voltage supply and fixing that. But now it's done, and the best part is, you are still here and you made it all the way through the video. So you're awesome, thanks for that. Yeah, here it's very nicely visible how crooked the motor is. I suspect because of the gearbox. There's huge amount of play in there. I can rock it back and forth. I mean, I can rotate it and wiggle it quite a bit, and then even can rock the axis back and forth quite substantially, which for the specification that I had in the beginning for precise motion is the death. So poor choice from the get-go. If you ask me how to improve, obviously I would rip out the motor and throw it out of the window immediately. Replace it with a directly driven NEMA 17, for example, in the pancake version, a very small one, and check out if that is up to the task, rotating that stuff. The only other thing that I would definitely change in the future is the power supply and also maybe the cable management for aesthetics. As I said in the video, I just printed different versions of the gears to cover the different speed regimes because the motor is not capable of going very slow and also very fast at the same time, because then it's skipping steps and it's just not working fine. So I print different sizes, and if I want to have it really slow, I take the really slow version with the small gear at the motor and larger one, not a larger one, also a small one on the, whatever, on the small one on the motor. And if I want to have a faster one, then I take a bigger one at the motor. If you want to remake this, the 3D model of this is available on Prusa Printables, and the code is available on Github for downloading. I will put the links in the description box below. If you do so, please share a remake maybe on Prusa Printables so I can actually see that and enjoy you remaking that. This one is done. I'm done. I'm out. I'm Bushi. Have a good one. See you soon. Bye. I like to keep things simple. That sounds like a rap. I like to keep things simple. Subscribe, and then you don't miss out the other cool things that I've planned. And it's empty, I just realized. Okay, just imagine there's a huge great light. Chapter 4. The build. Ah, we are through. Nice. I didn't know that.